And today, I will be talking about data-driven fine manipulation. So we want to push boundaries of what robots are capable of. And we will be focusing on this fine manipulation challenge that we want to design autonomous robotic system to grasp or move small objects. And we want to focus or hyper-focus on problems that are very sensitive to errors. We hope to use this problem domain and a platform that we have built as an accessible test bed to push in general the boundary for data-driven robotic learning system and to see what we can achieve. To give you an overview of today's talk, we will take a dive into the problem of fine manipulation, trying to characterize it, trying to motivate why it is an important problem. We will give you more details about the test bed, the robotic system that we have built. And then I will go deeper into two attempts. One's from imitation learning side of things, and the other is to use reinforcement learning to build the system. So let's begin. So for those of you who haven't thought about this fine manipulation problem, I want to give you a closer look on why this thing is hard. So as a human, we have a unique advantage of having fingers, and we actually deal with fine manipulation problems in our daily life very frequently. But even with humans' impressive capability of learning, things might still go wrong. So we can look at this example that we were trying to take out eggshells from broken egg whites, that we realize that the grasp here needs to be very, very precise. It might fail with even a sub-millimeter degree of errors. And moreover, like every time we fail, we move the object a little bit in this unknown fluid. So what's important here is really to achieve precision and reactivity at the same time. So similarly, a lot of tasks in our daily life carries the same flavor, like lock this necklace, grasping this food, harvesting, or doing surgery. So dexterous fine manipulation have a lot of applications, both in a home robot setting and in industrial manufacturing. So in the home setting, we listed a bunch of tasks here where you can see that since the human environments are built with a human-centric goal, a lot of things that humans can do are dexterous fine manipulation, and therefore to automate them or to handle those tasks, they naturally carry the flavor of fine manipulation. And then in the manufacturing side of things, there's a lot of tasks that are just sensitive to precision. Like if we look here, we gotta grasp this very, very, very tiny units, and there's a lot of assembly involved. And some of the tasks shown in the middle, the people assembly watch, are still done by humans. Now, we actually have quite some automated system in the industrial manufacturing side. But the typical pipeline that's existing right now are mostly highly scripted, which means that the hardware is relatively rigid, infrastructure are specialized for a certain task. It's kind of questionable whether any system can be applied to any fine-grained task in this flexible way. And at the end of the day, the system might be quite expensive. So that's partially the reason why some of the manufacturing tasks are still done by human. But what we want to do, since we want to push the boundary, is to ask ourselves, can we build a future generation that's autonomously doing fine manipulation with perhaps more affordable hardware that's more cost efficient? And then perhaps we want to conduct the task in a more dynamic, not so rigid, and also pretty efficient strategy. And then we also are curious if at some point we will be able to create very dexterous manipulator that can be adaptive to like motions required, can also generalize to few more tasks than what we're seeing here, where it's right now it's just like a single task, a single system. So we hope that this attempt to push the boundary will enable lower cost of entry into manufacturing or even home robots. We also hope that the dynamic and dexterous strategy would allow us to have faster turnaround on manufacturing or assistant robot service. So towards this end, we built a test bed. We have solicited some general purpose robot actuators and we just put them together. So we built a hardware that is very adaptive, like the shape can be changed at any time. And also it's pretty accessible, just assembled from some Lego-ish components called heavy robot actuators. So with this test bed, it's hardly surprising that our hardware has compounding errors due to assemble errors, mechanical being not so accurate, there's latency, there's actuator reading, there's also the fun story that if you collect data on the hardware in the winter, you better finish that project as soon as possible because in the summertime, your data may no longer applied because of a temperature change would affect your electricity output. There's a lot of things fluctuating in real world robotics. And we think this hardware, despite being low cost hardware and has its own compounding error issues, it's a good representative test bed that have all the problems that any robot system would face, regardless of being expensive or affordable. So with this hardware here, we can actually design some dexterous dynamic fine manipulation task. For example, shown here is this little ball swing in the air. It's a pretty hard task that I personally find difficult to do. And the goal then is, can we use this test bed to design some policy that's robust enough for significant amount of real world use? So we think that this is a good test bed because compared to previous approach, we think that in previous approaches, a lot of expensive hardware components are used, like either the actuations are very fancy or the camera, the perception system are dedicated, versus in our system, we use more generic hardware and affordable cameras. We also seen a pattern that in previous approaches, there are a lot of human burden in the system design, like human expert who are robotics researchers like you and me have to use their domain knowledge to design accurate modeling, to spend days on GAN tuning for each robot. And we hope that in our proposal or in our system, we would be able to design system that get away with that. We just want to be lazy as possible. We want to reduce the human efforts or the expert knowledge required in the process of building an autonomous system. So in a sense, we're facing a very general problem here that when we have a robotic system that needs to be deployed to a complex real world to face unknown, to solve a certain task, but also in face of unknown elements like physics, context, wear and tear over time, can we build a system that is capable of autonomously solve the task? For example, autonomous fine manipulation, and also a system for continually improving itself. I think this general goal is universal across not just fine manipulation, but also manipulation and even like navigation scenario. Now, since we are focusing on fine manipulation and we have built a test bed, we want to push the boundary on this task as a representative step towards this future. Now, for a fine manipulation task, we actually need to choose a fine manipulator. So robotists have built various effectors ranging from this complex hand on the left side, or simple tools on the right side. But in general, the simpler tools are more accessible, which fits what we're looking for and satisfy our need to be a test bed. But we also realize that not all simple tools are created equally. Not all simple tools can solve all problems. It can be hard to use a fork, for example, to grasp a bone. So simple tools might have limited applicability. That is a motivation of us to use chopsticks because we realize that simple tools might have limited applicability. Using a simple tool means that we transfer the challenge on the mechanical design to designing a controller strategy for using the simple tool. And we also need to ensure that the simple tools we have picked are versatile and can be applied very generally. So what we have seen here is chopsticks is actually both simple, versatile, and versatile because the shape of them are easy to model, represent, and control. So humans have demonstrated quite a wild use case using chopsticks. See here, a wildly dexterous humans actually used it to pickpocket using chopsticks. So on the other hand, we also believe that the shape of chopsticks are quite representative of this whole family of thumb-shaped grippers. So if you look at the bottom row, we see this as a surgical robot. And we also listed this alignment of tools that's widely used by surgical robots. And what we see here is a pattern that, unlike the parallel gripper that's widely seen in industrial right now, it's opening and closing at a parallel angle. This thumb-shaped, like tweezer-shaped tools are actually much more widely seen in this fine manipulation scenario. So that's also a motivation for us to choose chopsticks, because what we learned here can perhaps motivate the development of autonomous surgical robots. So now we have built our test bed and picked our fine manipulator. Let's take a closer look at the problem that we're trying to solve. So this is abstraction of the problem. So we have a manipulator, it's trying to approach and grasp this very challenging item, and it would have failed with sub-millimeter degree of errors. We see here that the agent shakes and then it misses the ideal grasping point by the way, the size of this ball is about 7 millimeters. So that's a sub-millimeter error, and that would lead to the failure on the task. And does this mean like there's too many inaccuracy in the hardware that we're not able to solve it? Like, how do we know if the test bed we built is even capable of solving this task? So we actually first run a proof of concept experiment to ask human to be our operator. So we observed impressive success picking up anything we can think of if we put human on the controller seat. So here are demos from a human expert teleoperating our hardware platform and to grasp like tiny object, deformable object in a crowded, clustered scene. Now, we know that humans are great. Humans are good at learning. And this actually opened up a whole landscape to collect demonstrations from humans since they're so good at learning. We thus launched our first attempt to automate this task, which is to just learn from human expert demonstrations. So we first launched a human study inviting people with varying expertise with chopsticks to come and use our platform and trying to teleoperate it without being previously trained, to just use our robot platform for about like 15 minutes and give us some data. So we did observe pretty crazy learning capability on the human controller, so that most people were able at the end of the 10 minutes trial, pick up all the objects we can throw at them. But to use a human data and then to learn from them a strategy to pick up this thing autonomously actually is non-trivial. What we observed here is once we collect the human data as shown on the top left and put them into a buffer, we then can reduce the problem we're facing to a supervised learning almost, because humans have provided trajectories. The trajectories are composed of state and action. And now we just need to learn a mapping from the current state to a desirable action. So we have input and labels. If we just run behavior cloning, the most simple form of imitation learning, but also the most widely used form because it's so simple, like almost everything else in imitation learning would require some more assumption added, but behavior cloning is something that you can always run, assuming you have this mapping. So once we run behavior cloning, what we hope to see was a black curve here. We were hoping that, hey, we collected this expert trajectories and we have learned the mapping and the training errors look great. They look like they converged. We were hoping that when we roll out the learner in the environment, we will be able to solve the task, just like the expert did. But the reality is that when we roll out the learner, we actually get this dotted line. So dotted line is slowly deviating from the expert trajectories. And this is actually a critical issue for imitation learning, which is coined as covariant shift. That there's also theoretical work suggesting that it's almost unavoidable that when you have an agent that can make any tiny amount of mistakes, that errors can compound quadratically with your horizon. So if we're driving, let's say in the autonomous driving scene, maybe your expert has only demonstrated how to drive on safe road, and because they're expert, they're so good at it. Or like similarly for drone flying, like all the experts are so good at some task, they do the optimal thing, and then your agents make one single mistakes, like I caught behind the tree, or I hit the side of the road, and then that error can soon compound because the agent is uninformed in any region that's outside the expert data. So for a manipulation task, you might wonder, so what does the error look like? In our manipulation setting, if we're going to take a slightly deeper dive on the hardware infra building, we would see that any robotic arm might have message latency and joint backlash. So if you don't work on hardware, this terms might sound a little bit strange, but in short, in each actuation joint that you use to assemble the robot arm, the reading and the command might have a small mismatch depending on the type of motor you use. And since we use gear motor, we have this joint backlash problem that the gear is slightly mismatched. So a tiny, tiny mismatch, like a 0.25 degree at the root of the robot, would translate to about 3 to 5 centimeter of mismatch at the tip of the robot manipulator. We have done some extra work to alleviate them, which I won't go too deep into now, but even with all the efforts on the data-driven method we have designed to help compounding such inaccuracy in your modeling, what we get eventually is this thing that because of the task precision, the task is so sensitive to precision, even when you have a successful expert demonstration and you replay it using exactly the same everything, the replay might not be 100% successful just because of the requirement of the precision. Now, that explain or is one example of the compounding inaccuracies that's specific to this problem domain, but how do we handle them? How do we work around it? So in general, we have observed that compounding errors can happen when a learner ventured off from an expert demonstrated region. So then we ask, can we figure out a way to generate what we call the corrective labels to help bring the learners back onto the expert demonstrated regions? So this is a desirable kind of label that we hope to generate. Now, we have to acknowledge that there are some previous work that also solicit corrective labels, but many of them are doing so by asking the expert. So the famous dagger algorithm, they would roll out the learner and then ask the expert, hey, I think I went to some place that's not demonstrated by you. Can you give me more labels? Or there's also some other work like DART, which interfere with the data collection process. So like before you even collected the data, they have some algorithm that encourage the data collection process to cover those states that otherwise the expert probably is not going into. But the goal of our proposal is not to bother the expert. We just want to ask that we have given an offline set of data. Can we generate some corrective labels from this set of data and this set of data only? What we did actually as a first attempt was very simple. After we collected the data, and then in training behavior cloning, we inject noise into the state input. And this gives us some successful trajectories, both in simulator and in the real world. And you might be surprised to learn that in the real world, the success rate boost is crazy. We observed that with or without the noise injection, the success rate of our system got boosted from like 30% to 60% on the real robot hardware. And you might also ask, hey, what's so cool about noise injection? Everyone has been doing it for decades. So something that's slightly hinting here is, we know that in a lot of other domains like vision, we have seen a lot of data augmentation, which includes noise injection. And it's kind of intuitively making sense that if I have this image and I'm going to put some like Gaussian noise onto this image, but I believe the information captured in this input are still preserved despite me injecting some noise. But in robotics, because our labels are like an action label that's designed for a state, it's a little bit surprising that if you disturb the state by some small amount of noise, you're actually able to reuse that action label. And like training that way actually improves the robustness of your imitation learning agents. So this is a very empirical work that showed that to combat current shift, you could actually figure out a training loss function to increase the robustness of your agents. But we're also interested in developing a framework to hopefully augment your data set with corrective labels. So if we're going to take a step back and look at what we have here, we know that we are given some expert demonstrations, and we know that a problem that we face is distributional shift or current shift when we roll out a learner. And what we desired is to generate corrective labels to bring a learner back to expert visited region, because we don't know anything else about any other states. Only thing we know is what did the expert does. So we want to go to the place that expert has visited, which means we at least have something to mimic at those states. So even though we used behavior cloning as illustration in all our experiments, we believe this data augmentation method are general for any other RL methods because we merely produce more labels. So we have seen in the last work that, hey, if you just inject noise, like shown illustrated in this graph, that if you collected some demonstrations and you take any state you have, you inject some noise, you get some fake augmented states, you reuse your action labels. This is a legit way to generate corrective labels. But can we have something that's more systematic, that's more than empirical results? So that launched the second attempt that we have. What we noticed here is that the noise BC, this proposal here, it would only work in a limited scenario where your action is invariance to the small disturbance. So what does that mean? So if you use positional control, like if this is a car that's positional controlled, it makes sense that if I'm tilted a little bit, then I still want to go back to the same position. But if the robot is controlled by a different interface, for example, torque control, such assumption of invariance might not hold and noise BC might fail to apply. So what we're trying to do instead is to learn a model from the given demonstrations, and we are going to use this learned model to generate corrective labels. So some of my question, what's the difference between this and model-based reinforcement? Because if you have a lot of data, why don't we just fit a model, fit a dynamics model, and then we can run like model-based control or model-based reinforcement learning. So we have to be actually very careful in using a learned model. So if we have all the data in the world and we build a great dynamics model of the world or of the task, then of course we can use or rely on a model-based approach to solve things. But here in imitation learning paradigm, we actually know that our data, the expert data, only covers the region that the expert cared about. So our learned model, which was trained from that data, is probably also not going to work very well if we ventured away from the expert place. So when we use such a learned model to generate corrective labels, and let's say we generate something for this Like, let's say like we have shown them how to drive in the USA, and then now I'm going to use a learned model to generate the data. That's like how to go back from Europe to USA using car. I don't know if that's possible. And I couldn't trust anything that the learned model have saying in this out of distribution scenario. So is this still a valid proposal? Like, can we still generate corrective labels from a learned dynamics model? We believe the answer is yes. So what we find out is that if we really zoom into the expert trajectory, like really zoom in and look at what is close to the data support, we believe that, well, if my expert has shown me how to drive from Seattle to Oregon, then maybe if I zoom in just close enough, I will be able to use the learned dynamics model to generate a data point for driving from like my school to Oregon or my home to Oregon. So we believe that once we zoom into the state space, like once we start seeing some continuity in the dynamics, we'll be able to actually bond the quality of the learned dynamics and therefore generate corrective labels that also have quality bond. So I won't go deep into the theoretical proof, but at the end of the day, we're able to show that, hey, if your environment dynamics have local Lipschitz continuity, you can then use a learned dynamics to generate correct labels, and your label would have a bounded error as well. Now, to give you a high-level intuition, so something you can take away is, let's say we have collected this blue curve demonstration, and we know that we have done, the expert have done some action at some state, and we just tweak that action by a tiny bit, like adding a small noise of delta, and then we can use a backward Euler coupled with the learned dynamics model to come up with generated state and generated action. And when the assumption is satisfied, this generated state SG and then executing your generated action AG will actually lead you back with some confidence back to the expert relative states. We then go test it out. So we tested out on a few different environments like pendulum, drone, Mojoko, meta word, and this 2D navigation task. So we noticed that the assumption that we have added, that the dynamics have some continuity, is something that we believe intuitively are true, because if the word is completely disjoint, it will be weird because then any movement is non-continuous. But in certain state representation, like a LiDAR navigation shown on the bottom left, it still left a question like, is there any continuity in such a domain? So we have tried this approach on a wide variety of tasks and found that for this kind of navigation task using disjoint LiDAR signal, actually there are some continuity that we were able to leverage, and our proposal CCIL beat both naive beer cloning and noise beer cloning. But on some other tasks like this meta word, which is a manipulation task with a lot of context, with a lot of friction and a lot of discontinuity in the joint state space, the performance can vary. So it varies across task to task. So we're in the middle of trying to write this up, but I think the general takeaway is interesting that if we zoom in close enough and leverage local continuity, we'll be able to generate corrective labels, almost similar to how stabilizing control literature uses a local model to, to just put the agent back to a known place.
Okay. Hey, Kay, do you mind if I ask a question?
Yeah, sure.
You hear me? Great. One of the parts I was wondering about that I would have to deal with some of the assumptions of the method. Like, it seems like if there was a really large time step in the control structure for the agent, then it's going to have like larger distances or possible variances it'll have to learn to cover over. So have you tried varying, like the control speed or the frequency?
Interesting. So for the imitation learning task, we didn't vary it for the simulator, but for the real robot, it's something that's very sensitive, and we did try vary it. We for our hardware, we find this thing that's kind of straightforward. I don't know what caveat is in for other domains, but for our problem, we for imitation learning, we really like to increase the control frequency. So like our hardware supports 500 to 1,000 hertz high frequency control. For imitation learning stack, we actually ended up using about 200 hertz or 100 hertz, in contrast to many other people's manipulator task that has 5 hertz. And the reason of us doing so is because there's this very interesting observation that once you change the control frequency, you actually change the amount of data you get from the same length of trajectory. Like 5 seconds will be translated to like 25 steps if you're running some like low frequency control. But if you're running a high frequency control, 5 seconds means like 500 or 5,000 steps, data points. So for our problem domain, it seems very beneficial to increase control frequency such that you get more data coverage. Is that answering your question, or?
Yeah, that answers my question. I guess I was wondering, like when you increase the control frequency, you sort of don't get as diverse data. The difference between certain points are going to be millimeters now instead of centimeters. And interpreting them, you also would require your agent to compute more actions more quickly. So this might work well for deep learning. Yeah. But it would struggle if there was more like a planning algorithm in the background that needs to replan at all these steps.
Oh yeah. A flavor of my current research for sure, like good to notice that is I felt that I'm actually competing more with the controller side of things. I feel that it's for the task I'm considering right now, it is actually conceptually relatively simple. Like let's say we are a planner, and let's say that we look at the task that we care about, we just want to grasp this ball. It's relatively easy for like a planner to tell us that, oh, you're grasping a ball. These are the 2 points you need to reach, and then you execute the grasp. Like like that's doable part. And then what's challenging in this task that I picked was to execute that plan. So like to really push the controller, push the controller accuracy. And therefore, that's perhaps why right now my research carries a flavor of let's run slightly higher frequency control. But it will be interesting to, I guess, once you have a high level plan or a low frequency control high level plan, you will probably be able to handle much longer horizon task. And that will be interesting to study.
Okay, thank you.
Yeah. Go ahead. So I assume no one else has a question? Okay, let me continue then. So this summarizes our attempt on generating corrective labels for imitation learning when you have a fixed set of data set. How do you squeeze the juice out of it? But there's still some challenge in running this sort of imitation learning algorithm that because you inevitably are learning from the fixed set of data. So if we want to succeed, we really have to ensure the data covers all the variants of the task. And there can be a lot of variants, like the easy variants are, hey, what if the ball are placed at different location? What if the ball's materials are different? What if it's not a ball? What if it's a different shaped object? And there's some harder variants to collect. For example, like if we start moving the object at some random initial velocity, and if we want to cover that and then couple with all the other dimensions of variance, the amount of data that will be required would grow exponentially. So we find it very challenging, and we kind of come to believe that for a given task, it is possible that one cannot collect all the variance of the task, and we just cannot afford that. So can we increase or make the system learn beyond a given set of demonstration? So we go back now to our human study and what we see there, and pointed out that there's this interesting behavior called adapting to failures. So what is happening here is when the human are operating the robots, we don't stop the trial upon their failure. Like you can see their teleoperation, they're touching the object a lot, they're not getting it up. We actually let the subject continue interacting with the object after failure for almost 20 seconds. This is very different from a rigidly scripted robotic system where a lot of times success are judged by one shot. So like it's like a cloud machine that you go there, you fail, and that's considered failure. Like we actually let it keep trying. And by allowing people to keep trying, we observe some crazy success rate. So here's an example task, an example retrying. But if we look at the statistical report on the right-hand side, for the 5 objects we have considered, the blue bar is the one-shot success. And we can see here, this glass ball is a very challenging task. And the one-shot success rate is about 26% from human expert. But if only you allow the subject to keep trying, 80% of the trial, 80% of the trial would succeed. It's just extending the trial to 20 seconds. So we believe that this is a very useful feature to have in fine manipulation domain, that even when failure happens, can the system demonstrate robustness by reacting and adjusting its own strategy. So this has prompted us to design first an antipodal grasping plus visual serving baseline. So if I'm a human and I'm adjusting my strategy, what I'm going to do is I'm trying to match my chopstick tip to the object. And by the way, this worked pretty well on static scenario and then scenario with tiny amount of motion, but it kind of fell on large motion task. So the reason of our failures partially comes from the hardware limitation that, hey, it's kind of hard to match the human intuition with the limited perception system we have. Because humans are very fast in perceiving like, hey, the tip is here, the ball is there, I need to do something. But for us, we only have a 20 hertz off the shelf camera. And also beyond that, there's also non-trivial GAN tuning that we spend like 2 or 3 hours designing this policy and GAN tune it to make sure it works on even the more limited version of scenario. But also, we also question if the human strategy is the optimal strategy for this task. So we would like to build a continually improving system for this task that prompt us to reinforcement learning. And in general, reinforcement learning assume unknown model. They completely collect and rely on data to learn control strategies. So famous reinforcement learning algorithms include PPO or SAC. And we have seen success of reinforcement learning algorithms, for example, on AlphaGo, in the multiple simulator, and notably in the real world, Google has launched this QT-OPT work that involved hundreds of robots and thousands of, I don't know, like my lifetimes training data. And with the right amount and kind of data, it does seem that reinforcement learning could figure out good control strategies. The question for us then is, can we build a reinforcement learning system successful for our platform? And as the first step, we would just deploy the reinforcement learning system in simulator, and this is what it would look like, that your robot just do random stuff. We noticed that to apply reinforcement learning to the real world, there's quite some challenge. So the first one is the reset challenge, that reinforcement learning needs to explore how to solve the task. They need to be able to fail. And after they fail, someone have to go there and reset the thing so that they can try again. It's like babysitting, but worse, because this baby is, I don't know, it's not as clever as human baby. So that's actually one of the biggest issue in applying reinforcement learning on real robot system, that how do we get this reset? It's costly. Well, it costs too many PhD students to do it. And the second question of reinforcement learning is sample efficiency. So how much time does a reinforcement learning agent in the real world take to learn some strategy? Like the previous state of the art almost all involve like 20, 30, 40, 50, 60 hours to learn this strategy to grasp this thing up. there's also a question on precision. So no one has applied reinforcement learning for a task that's as precise as what we need here, because most of the precision in the previous reinforcement learning system are like centimeter level, but we care about sub-millimeter level of precision. So we went ahead and then designed a system that achieved some pretty impressive results that we'd like to share with you. So the highlight of our work is a system that uses reinforcement learning for cherry picking. And the system need only about 30 minutes of real world data. And it demonstrates quite some robustness and reactivity and fine manipulation capability despite using only limited real world data. So how do we achieve it is actually through the simple insight. We didn't invent some fancy novel reinforcement learning algorithm. We actually build instead a system that leverages prior information appropriately. So we believe that there's a lot of prior information on robotics that are available to us. So like when we think about reinforcement learning, we shouldn't be limiting ourselves to the, hey, we train this in simulator, we're model free, then we don't have a model. But in reality, for a robotic system, there's so many information available, and combining them together and finding better way to combining them, I think is a very valuable research direction. Like, for example, in this work, we just scrapped everything that any robotics would build for the robot. Like there's a simulator, we know it's not a good simulator, but if you have built a robot, you probably well build a kinematic model for that robot at least. And it's an approximate simulator that won't allow you to run model-based control and solve the task, but it's a simulator. Similarly, you can hard code some demonstration. Maybe your demo policy has only 2% success rate, but that's enough for collecting demonstration. And similarly, we can leverage all the post-estimation perception literature for some state estimation that's noisy, that we know is not tailored for your task, but those are available. And maybe we should find a way to put them together. So that inspired our reinforcement learning system that can be break down to 3 stages. There's pre-training, there's fine-tuning, there's test. And we're gonna go take a deeper look into each of them. So in the first stage of pre-training, we use an approximate simulator model and heuristic baseline. So without pre-training, by the way, I don't think this reinforcement learning system is ever going to work, because we run them for 20 hours. That's a blue curve shown on the bottom. It's hopeless. It's just constantly hitting the safety check. But with pre-training, it's actually able to make progress. Now, when we're using the simulator model, because it's approximate, we actually disturb the dynamics parameter in the simulator to encourage the policy to be robust to the dynamic parameters. We also put a heuristic baseline and actually found out that even though reinforcement learning claim that they don't need any demonstration, if you put the demonstration, no matter how bad it is or good it is or how many you have, put that in the replay buffer of the reinforcement learning agent, you get much better results. So here is a plot we showed aggregating over 10 random seeds. So you can see how without demonstration, the blue curve has high variance. Actually, many of the random seeds without demonstration just failed to learn a task, even in simulator.
One quick question about the demonstration you're adding.
Yes.
That's okay. So if it's a demonstration, where do you get the rewards from to label these demonstration objective?
So because in reinforcement learning, we need access to the reward function. So for all the reinforcement learning literature, you just hand design a reward function. So for ours, in simulator, it's very easy. In simulator, you want to grasp this thing, okay, what's the position of that thing? Are you getting closer? So you design a cost function like that. And then the demonstration itself actually comes from the previous baseline we built, the antipodal grasping plus visual serving baseline, which has about 80% success rate on static scene, but like 20% on dynamic scene. We just run it for a while, collect some demonstration.
Okay, thank you.
Okay. So yeah, so because we have access to the reward function, you can almost throw in any arbitrary examples. Like it doesn't even need to be for your task. You can always throw that and then use your reward function to label them, to give them the reward, and then you can put them in the buffer and use them. And we find that this is very helpful for reinforcement learning algorithm training, even in simulator. Now, a side note that's interesting that I think people might think can be inspiring is when we assume this are the assumptions we're working with, that we have demonstration data, we have simulator, we also have a real world fine-tuning stage, we got to choose a reinforcement learning algorithm that can eventually help us fine-tune. And contrary to popular belief, which says that offline reinforcement learning should be the thing we choose, we actually find out that traditional off-policy reinforcement learning algorithms like SAC is actually better or demonstrated stronger capability in fine-tuning than a corresponding part from offline reinforcement learning family like IQL. So if we look here, that the blue curve is in the pre-training stage indeed makes some progress, but in the fine-tuning stage was struggling. And on the contrary, the SAC was quickly learning once it started collecting data and then use it to fine-tune itself. So now we have in the simulator pre-trained a policy that is pretty robust to any variations we can throw at it in the simulator. We need to fine-tune it in the real world. Now, to fine-tune it in the real world, this is what you get when you put that agent on the real world in the first iteration. It's just doing, I don't know what it is doing. It's missing the object. It's not really what we wanted. It's pretty hopeless at the task. So in order to fine-tune this, we want to devise reset mechanism, and we want to boost the time it would take to fine-tune. So the reset mechanism is pretty obvious from this picture. We put a ball that's on a string so that I can go to school and then I can go home and sleep while this agent learns. So this is a domain-specific reset mechanism, but we think it's pretty general for any grasping task. And perhaps other people would realize that there's some philosophy in choosing this task that can be reused that we'll talk about later. But in short, our reset mechanism makes this problem pretty hard, makes the ball pretty dynamic, and then have some random initial velocity, which encourages the policy to be robust. Now, the second aspect of real-world fine-tuning is to boost the walk clock time efficiency, which it's kind of interesting that it's not something that people who only does RL in the simulator pay attention to, because in simulator RL, many people assume that, hey, I collect one environment step, and then I run one policy update, and that's my sample efficiency. But in the real world, we care more about walk clock time efficiency, which means that given this time, I can use it to collect word demonstration data. We can also use it to run policy update. What ended up happening here that we did is to run this asynchronized update. So for every data point we collected, we effectively committed 10 policy updates. And that in the real world means a 3-time difference in the time it takes to train. Now, to verify or to show that our system, cherry picking system, is not actually cherry picked, we also run it on 3 different random seeds in the real world. And the algorithm and code base we used are actually just git clone from a public available library. We used all default hyperparameter, and this is 3 random seeds in the real world. So we're convinced that this training paradigm is very reproducible and have similar clock time efficiency across random seeds. All of this system take about 30 to 40 minutes of real world data to learn. Now, after the fine-tuning stage or at the end of it, we can see that the system has consistent 100% success rate picking up this ball, even though the ball might be swinging around. Now we'll have to deploy the system to the real world. So in the deployment, we will rely on perception modular that might be noisy, but we can plug in any perception modular to be deployed to a diverse scene. So here we show an example of, hey, we want to grasp this cherry that's floating in the water. And if you hit the cup before you approach them, you can see the cherry have this small like vibration motion. And when we deploy deploy our system to also like more diverse scene here, you can see like it might even fail because the perception modular is not super accurate. You can see we use segmentation modular here to grasp to get the object position. But as long as the agent is given the chance to retry, and it's capable of adjusting its own mistakes. Now, we also test the robustness of our system against dynamic disturbance. This is where the visual servo baseline failed. So in the visual servo baseline, remember, because we tuned again for a certain scenario. So when we inject disturbance, the visual servo would only work if we spend more time to tune again for the new scenario. But for this learned system, we actually are able to be robust to a certain level of dynamic disturbance out of the box. So you see the performance here is that the system actually developed its own strategy in grasping this moving, shaking, disturbed ball, unlike the visual servo, which was just trying to like match it like what a human would do. The learning system has its own interesting trial that we will show in the slow motion on the next slide. But in short, the robustness to dynamic disturbance demonstrated by the learning system is something that just happened by the appropriate design of the task, not a burdening on the human expert to do the gain tuning. Now, to show you an interesting video, so this is a slow motion of what is happening with the agent. You can see like in the middle, the agent was trying to touch the cherry to grasp, but it failed and it's constantly adjusting. That's actually the novel strategy the agent demonstrated. And the reason of why it needs to do that adjustment is actually because of the perception noise. So we, in this one, I think we use YOLO. And if you ever used YOLO, you know that regression-based detection network is not the most accurate thing in the world. They constantly shakes. And that created some problem for fine manipulation, actually a critical problem for fine manipulation, that the agent then just have like this whole confusing, like where is the object signal? And the task we have chose right now, since it allows you to retry, so we show that the agent actually has its own strategy of being robust against perception noise by continual retry. So our system, well, it might not generalize to all objects at all time, but it has pretty decent performance here, showing on generalizing to grasp objects with different textures, shapes, deformable or not, size, friction, dynamic movement. The success rate of this whole set is about 64%. So to conclude, this is a system that is continually learning, and we hope that we will build on top of this to push the boundary of dexterous fine manipulation. Something interesting for reinforcement learning folks to think about is we actually trained on, like the training task we have is not the downstream task we are wanting to test on. It's actually harder than our downstream task. So we train on a harder task. We actually get some robust deployment to simpler task at test time. And an overall message we hope people can take away from this is a good system design actually can reduce requirements on the hardware and human efforts. And we hope that would help automate fine manipulation in industrial and daily lives. Any questions? Okay, and that concludes my talk. I have to say thanks to my advisor, Siddhartha Srinivasa, and all my collaborators, because robots is fundamentally a team effort. Couldn't make it here without all my collaborators. And I'm happy to take more questions.
Yeah, thank you. I guess I definitely had one quick question that I was wondering about. Because you're doing really delicate manipulation tasks.
Yes.
What were you using as the sensors to be able to determine locations? Was that like a motion capture set, or did you have some particular like cameras you were using?
So since this reinforcement learning system has 3 stages, in the training stage, we use a motion capture system. In the test stage, because we want to generalize to things and different objects and scenarios, we used the Azure camera, and we plugged in different perception modular. to that system. So the camera is shown here. It's an RGBD camera. It costs like $500. It gives us about 20 hertz RGB data. We choose it over Intel RealSense because the depth sensing on this camera is better. But still, they're all like cheap off-the-shelf option. Now, to deploy it to different tasks, the perception modular might be slightly different. We actually have three things we tried in the paper. So one is a very simple heuristic-based thing. Hey, you do a saliency test, and then you just grasp the most popping color like of your choice. You choose yellow. Okay, we're going to figure out where the yellow centroid of the yellow color is. So that's one way. The second is YOLO. So that's this thing. Like here it's done by YOLO. So again, trying to based on YOLO's detection result, finding the center point, finding the depths, and then project it back to where the object probably is. And then there's also an early attempt of trying to use segmentation network. This one is a little bit tricky. We try to use the most fancy segmentation network lately, the SAM, Segment Anything by Facebook. The downside of that segmentation modular is that they run super slow. So they cannot be run in real time. So there's almost this trade-off between how accurate something can be versus how high frequency or fast something can run, to help us be a closed loop controller. So in this, we try to use SAM, and the speed of that was not satisfying. I think we ended up using something similar with some tracking capability. Yeah, but essentially we use off-shelf perception modules.
Okay, thank you. Other questions? Okay. We'll pause there for now. Say thank you very much for giving a talk today. It's very delicate and interesting work. Being able to get something so accurate is very impressive.
Hey, thank you for inviting. I'm also pushing some more threads since I mentioned in the talk that there's some more like research threads happening. There's also like model building using data-driven methods. There's also some dynamics task, and there's also that corrective imitation learning thread or the offline RL thread. I'm happy to take questions or like correspondence through email, like if any of your group mates are interested. Okay.
Yeah. Sounds great. Thank you. Take care.
Okay. Thank you. Bye.
Thank you.